Hello, my name is Nicholas Verostegui, and the project I'm presenting today is called the Development of a Rust Language Compiler for the AFTx06 chip and Development of Sample Applications. So this project aims to create a Rust-based front end for the LLVM version used by Purdue's System-on-Chip team. This will run Rust-based LLVM code through several sparsity-supported passes. The passes will then go through the backend to produce machine code, with the final goal of this project being that machine code will then be ran on the AFTx06. Now, the AFTx06 is an application-specific integrated circuit. These integrated circuits design supports sparsity, but testing will be done on a field programmable gate array. Now, FPGA. An FPGA is a chip with reprogrammable logic, which is ideal for testing in the case that we decide to redesign the internal logic of the AFTx06, both of which will be running off a RISC-V core. Now, what RISC-V is a type of instruction set architecture, or ISA. ISAs specify machine code behavior. It would be easy to think about it as the interconnect between software and hardware. But what makes RISC-V unique is its stability and simplicity, and how it's cleaner and more cut compared to other architectures. This makes it faster and easier to manage. Our particular RISC-V implementation supports sparsity. Now, I mentioned LLVM, and what that means is low-level virtual machine. It's a project that consists of compiler and toolchain technology. As you can see in the diagram above, this is how a typical LLVM version works, with C or C++ compiled through Clang in the front end to output LLVM IR, or intermediate representation. This IR is then ran through several passes, which optimize the code as the programmer sees fit. Our particular version utilizes sparsity, which I'll explain momentarily. But what makes the passes unique to LLVM is that they're extremely modular and interchangeable, meaning that the programmers can change the passes themselves or insert new ones as they see fit. This IR is then compiled through the backend to output machine code. Now, I've mentioned sparsity, but what that is the ability to code to dynamically choose which instructions to execute. It can identify redundant code, and it does this by generating a sparsity-aware skip address or SASA table. These tables indicate which instructions can be skipped. A prominent example of how this would work would be in sparse matrix multiplication. A sparse matrix is a matrix where the numbers are mostly made up of zeros. So the ability of the code to identify which matrices are filled with zeros and choose dynamically which instructions not to execute would significantly increase the speed of the code. Now, why we want to use Rust is because it's a multi-paradigm language and a strong competitor with C and C++. It provides strong static guarantees, and it's significantly harder to make mistakes that are easy to make in C. For example, in C, it's a very common mistake to attempt to access memory that either you do not have access to or does not exist. Rust completely solves this issue. It gives precise control over data layout and memory management, but still retaining a high speed and stability comparable to C. Now, developing a Rust front end would help benchmark progress on the chip, as well as open opportunities for more sample applications on the chip, with machine learning being a prominent example. In addition, we hope to port a Rust-based operating system on the chip because it will help to create a more secure computer. How is this code developed? Well, you see, we used a custom LLVM version where Rust is compiled through the Rust-C compiler into LLVM IR. This LLVM IR was then compiled through the custom Clang compiler, or in this case, running it through each of the passes in LLVM to produce a SASA table for sparsity and assembly code which utilizes the Sasa table. This assembly code is then compiled through GCC and outputs machine code. And as a result, we were able to successfully admit LLVM IR, and this IR was compiled into the desired binaries, the ones compatible with the AFTx06 chip. A Sasa table was produced and a type state module was successfully implemented. However, we can only compile bare metal Rust. And what bare metal Rust means is that no preloaded code can currently be ran. So any references to a standard library or any external crates that most programmers would typically have access to when utilizing Rust are not available. This does significantly increase the limitations of what we can currently do with the Rust-based LLVM. However, future work will be done to include external libraries. But for right now, this is proof that a Rust-based operating system could be ran on the AFTx06. Here are my references. I'd like to thank Dr. Mark Johnson, Cole Nelson, John Martinick, G. Hu, and funding and the Scale program for this project. This concludes my presentation.